This is a video on an application of Snell's law, looking into what's called the critical angle. Okay, so you can get this really neat phenomenon occurring in things like fiber optics. Okay, so fiber optics are very delicate pieces of glass material with different layers wrapping around it. So fiber optics work, so light comes in and reflects inside it. Okay, and the advantage, one of the key advantages of using fiber optics instead of just electrical wires is that light travels faster than electricity, and so you've got more information going through. So from Snell's law, we know that n sub 1 sine theta 1 is n sub 2 sine theta 2. Okay, I'll draw a diagram. Let's suppose that that's air. Okay, and that's glass here. And that's the normal. Okay, air is a refractive index, let's say n sub 1, glass n sub 2. And so fiber optics work. So here's an incident ray. And the glass, of course, has a high refractive index, making some angle, theta sub 1, with the normal. And so when the angle of refraction, so when theta sub 2 is 90 degrees, the refracted ray emerges, comes out parallel to the interface, okay, at the boundary. So that's what happens to the refracted ray. Right. And this is known as the limiting case of refraction. Okay. And so let's substitute this into Snell's law. So n sub 1 sine theta 1 is n sub 2 sine 90 degrees. Now sine 90 degrees is just 1. Okay, and taking the limiting case in this, so in other words, theta sub 1, taking this to be called the critical angle, theta sub c, we get this, n sub 1 sine theta sub c is just n2. And solving for sine theta sub c, get n2 divided by n1. And to get theta sub c on its own, we take the inverse sine of both sides. And there we have a relationship, a formula to calculate the critical angle. Okay, which is the angle of incidence at which total internal reflection occurs. This is called total internal reflection here. Okay, light is being reflected. Okay, you can actually overcome refraction in a fiber optic, something like a fiber optic.